Today, we're going on a pretty incredible journey. We're going to map the human brain's network from the first days of life all the way to 100 years old. A brand new study has given us this unprecedented look at how our minds get built, how they peak, and how they fundamentally rewire themselves over our entire lifetime. So let's just start with a question that really affects every single one of us. How does the wiring of your brain actually evolve? Because it's not a static thing, right? It's this dynamic, living network that's constantly building, peaking, and reorganizing. Okay, so to really get this, we need to wrap our heads around one key term: functional connectivity. Now, don't think of it like the physical wires in a computer. It's more like the brain's invisible real-time traffic report. It's all about which parts of the brain are chatting with each other and working together from one moment to the next. So how does the brain organize all of this unbelievably complex traffic? Well, it's not chaos, not at all. It turns out there's a secret blueprint, a set of fundamental rules that govern how our mind is structured from the ground up. This new research has revealed that our brain's functional network is organized along three master gradients. Think of these like the core blueprints that create order. They shape literally everything, from how you feel a simple touch to how you can sit and ponder the meaning of the universe. Probably the easiest way to think about these three gradients is to imagine them as your brain's core operating system. Yeah, like Windows or Mac OS for your mind. Each one has a really distinct and absolutely crucial job in managing how you experience the world. Okay, first up is the sensory association, or SA gradient. This is basically the brain's main processor. It creates this amazing spectrum that runs all the way from the parts of your brain that handle direct sensory input, sight, sound, touch, to the high-level parts where abstract thought, planning, and memory happen. Next, we've got the visual-somatosensory, or VS, gradient. In our little computer analogy, this is like your brain's dedicated graphics and haptics cards. It creates a really clear separation between the networks that handle everything you see and the ones that manage bodily sensations like touch and movement. And finally, there's the modulation-representation, or MR gradient. This one is the resource manager. It's constantly allocating your brain's power, balancing between the systems you need for focused external tasks, like when you're solving a puzzle, and those that are more for internal thought, like when you're daydreaming. Okay, so now that we have our brain's operating system, let's see how it actually gets installed and updated over a lifetime, starting right from the very beginning. What's so cool is that the development follows this really clear, almost elegant pattern. It starts with simple, local wiring when you're an infant. Then it moves to a more globally integrated network in childhood. Adolescence is this intense period of fine-tuning. And then finally, early adulthood is when the brain hits its peak organizational complexity. At birth, the brain's network is pretty basic. The connections are mostly short-range, heavily focused within sensory areas for sight, sound, and touch. You can think of it like a brand new city that only has local neighborhood roads. No highways have been built yet. The brain is just laying its foundation first. And this slide here gives us a fascinating peek into that early state. You can just see how the activity's all clustered and not really integrated yet. The long-range superhighways that are going to define adult thinking, they just haven't been built. It's a brain that's very much under construction. But then, during childhood, this massive shift happens. Long-range connections start to pop up, bridging distant parts of the brain. And this is the crucial step, right? This is what allows for those higher-order networks, like the ones for self-reflection and decision-making, to finally come online. And this illustrates the result perfectly. Just compare this adolescent brain to the infant one we just saw. It's a night and day difference. The network is so much more interconnected, so much more global. This is the architecture that lets us do sophisticated thinking. The highways are now open, and traffic is flowing everywhere. So this period of intense development leads to a peak, a point where the brain's organizational complexity is at its absolute maximum. So the big question is, when does this peak actually happen? Get this. The magic number is around 19 years of age. That's when those key gradients for abstract thought and control, or SA and MR gradients, reach their maximum range. It's the biological peak. It's the moment our brain is most powerfully equipped for complex, integrated thought. This chart shows the different timelines just beautifully. Notice that classic inverted U-shaped journey. The sensory VS gradient on the left peaks really early, around age 5, which totally makes sense for a little kid exploring the world. But the SAMR gradients, the ones for higher level thought, they keep developing all through the teen years, peaking much later before they start this slow, gradual contraction. But the story doesn't just end at the peak. As we get older, the brain doesn't simply decline. It goes through what you could call a great rewiring. It actually adapts and changes its whole organizational strategy, moving from being highly specialized to being more integrated. And this comparison is just fantastic. In a peak adult brain, the networks are highly differentiated. They're like a team of specialists, each with a very specific job. But in the aging brain, a process called dedifferentiation happens. The sharp boundaries between those networks start to blur, and the regions become less specialized, working more collaboratively to get the job done. Okay, so mapping this entire lifespan journey is obviously fascinating, but it's not just an academic exercise. This blueprint has some profound, practical implications for medicine and for our own health. Let's dig into why this matters so much. Having this map is like having a GPS for the brain's development for the first time. It helps scientists predict cognitive performance and even pinpoint how things might go off track in disorders like autism or schizophrenia. It helps us understand what's happening in diseases like Alzheimer's. It gives us a baseline, a normal reference to finally chart a course for promoting healthy brain aging for everyone. And all of this leaves us with a really powerful question. Now that we have this incredible map of a healthy brain's journey from day 1 to year 100, what can we learn from it to better navigate and protect the health of our own minds throughout our entire lives? Thanks so much for watching. If you found this useful, please hit that like button and subscribe to Computational Genome Biology for more deep dives into the cutting edge of science.